We've talked about the celestial sphere and how the celestial sphere rotates around the Earth and how it looks like we're standing still while the stars rotate around us. Well, for thousands of years, it seemed really logical that the Earth was the center of the universe and everything revolved around it. Ancient Greek philosophers worked really hard on this problem, and they tried to come up with models to explain the motion of the heavens. The problem with that was the wandering planets. While the stars and everything else, and the moon and the sun all seemed to go in the same direction night after night after night, there was periods of time where some of the planets, specifically Jupiter, Mars, and Saturn, would appear to go the opposite direction. So this confounded them, but they still continued on with this model called the geocentric model, in which the Earth was the center of the universe. And this went on for thousands of years. Now, Ptolemy, it's called the Ptolemaic system. Ptolemy was a really, really bright guy. He was actually one of the first to postulate and measure the fact that the Earth was round, even though somehow we've got this myth in society that we believe the Earth was flat until Columbus sailed. That's not true at all, because Ptolemy and many others had worked that out in the past. So his geocentric model lasted for thousands of years. Thousands, and it was like the Bible, the astronomer's Bible. But some revolutions occurred later on to help explain that. But first, we're going to talk about what they observed, why there was still a problem that existed the whole time with the Ptolemaic system. Because we are inside, and I've drawn this sort of schematic diagram. I think there's one in the textbook as well. But this is the Earth in three different positions at three different times as it's going inside of Jupiter's orbit. So let's just have this Jupiter out here. Okay, that's Jupiter in red. So if I'm an observer on Earth and I look at Jupiter on one night and I trace my line of sight, it's going to go that direction. All right? Some time passes, a couple more days, and I'm at the second position. So this is after a couple of days. Position 2 corresponds to another day, right? So I'm going to trace that path, all right? Okay, so then I get to the third position here. This is another time later. Now the Earth is inside and it's moving faster, and this was not known. It was not known that the Earth was moving at all for a long time until Copernicus had the sun-centered model. Then it kind of started to make sense, but he still had problems, which I'll talk about in a second here. So then I get to this third position here and I trace this line of sight and I go through Jupiter, okay? So if I'm on Earth, it looks to me that position 1 was up here, position 2 was up here. Oops. Let's do this in black. Position 2, position 3. This is 1, 2, 3. So it looked like, instead of Jupiter actually moving this way, it looked from an observer on Earth over a series of like a month or so, it looked like Jupiter was actually moving the other way, which it wasn't. This was just an apparent shift. It's called parallax. So that's why the planets seem to wander. In fact, the word planet comes from wandering, from I think Latin, I believe, or Greek or something. I'm not sure. I'm not a linguist. But they wandered across the sky where all the other stars seem fixed. The planets, however, they would move differently than we would expect. So if I was to look in the night sky and plot night after night, it would look like it's moving along just like every other star in this direction, and then for a little bit it would look like it would come back a little bit, which was weird, and then it would start to go along in the same direction. So that's what, if I plotted night after night the direction in the sky, it looked like the planet was moving like that where the rest of the stars didn't. So they didn't really know what a planet was. They didn't have telescopes invented yet. So this was quite a mystery for a long time. So what they tried to do, and I've got like they tried to do is add these things called epicycles. Okay. Now this was an effort to explain why they moved back and forth. So this was kind of the same principle as this, but they didn't even know this yet. But it's the same principle as this, where it seemed like the planet would be going. The planet had an extra circle on the other circle, and not circles or ellipses. We'll talk about that in a second. But it looked like the planet had an extra ellipse to account for this. And the problem was that it was really arbitrary how the planets were assigned. And this continued to persist once Copernicus had the sun-centered model. He also still had problems. trying to fit it. So he added epicycles as well, and again it was still kind of arbitrary, and he still couldn't find the right explanation for why the planets moved the way they did, because he assumed they were circular orbits. Well, Tycho Brahe logged a lot of data. He actually believed in the geocentric model even though he was after Copernicus, but he logged a ton of data, which was a huge advancement for astronomy. So Kepler, who worked underneath Tycho Brahe, well, Tycho Brahe actually, it's rumored Tycho Brahe was a big party animal, so he would stay up all night observing and drinking and partying, and that's what he did night after night. I think it eventually even killed him. His drinking did. But Kepler was also a pretty crazy guy too. He was a mathematician, and he would talk about the harmony of the spheres, because he thought they were all on concentric spheres. So even though Copernicus said, oh, it revolves around that, revolves around the sun, and there's others that say no, it revolves around the earth, Kepler had this thing that he thought was the harmony of the spheres, and he thought it was music. He would look up in the sky, and to him he would actually hear music from these harmony of the spheres, and the spheres are what the planets traveled on to him. But he was trying to find a proper orbit that would work, that could explain the Copernican model that didn't include these epicycles, these really weird epicycles that have no purpose being there or no explanation as to why they're there. So after Kepler played around quite a bit with the data that Tycho Brahe accumulated, then he determined that planets actually travel in ellipses, and is able to actually meet the data quite well. So I'm going to go over here, movable table, yeah, that's high technology. So Kepler's first law: planets move in ellipses. So an ellipse is, if you want to think about it, like a squashed circle. Okay, so this actually accounted for, Kepler still didn't know the reason why. It was many years later with Newton, who kind of explained it. But the fact is that this ended up matching sort of what he was seeing in the sky, and was able to make predictions with it. Now an ellipse, this is just a mathematical ellipse here where I've got two focus. So it's determined by the two focus. One way to do this experimentally, I would have liked to do it in the lab, but we're on an online course, and then you have to get material. But you can take tacks, and you can put a tack at each one of these. So I can put a tack at each one of these, and then I can take some string here with a fixed length, so that the string will come out to here, here, and here. So it'll make it like a triangle, right? And if I take a pencil and I hold that string and trace it all the way around, as I move around, it's going to trace out this ellipse. Okay, so an ellipse is defined by the two focus. Okay, what Kepler said was that that planets move in ellipses with the sun at one of its focus. So this is an empty focus. This would be the sun. So this was here, imaginary, and this was the sun. But although it's still this relates to some gravity, which we'll get into next week. This relates to gravity, is why there's an empty focus there, and why they move in ellipses. So what he determined was that planets move in ellipses. So I'm going to talk a little bit about a basic ellipse, because we need this to understand going forward. So an ellipse is defined, there's numbers of ways to define ellipses, but what I like to do best for astronomy's sake and for Kepler's law's sake is this definition of eccentricity, which relates to the semi-major axis. So this is the semi-major axis, but this is the major axis from end to end. So from end to end is major axis. So halfway through that, to the center, is the semi-major axis. Okay, then this term C is the distance from the center to one of its foci. It's got very different names or whatever, but this distance from here to here is we call C. So we can define eccentricity. Just give me a second, I'll get a little more clear on this. We define eccentricity E, and we'll go equal to, and let's just keep these numbers. Let's just keep the colors the same. So we can define the eccentricity as C over A. What does this mean? Well, so if I take C down to 0, so that these focus come closer and closer, so if I take C down to 0, whoop, what I end up with is a very, very, very tight ellipse, almost a circle. So my foci, I should say, my foci really, really, really small. So let's try to make this more circular. Looks more like an egg. So this would be, my C then becomes like really tiny. So my C will be from here to here. From one of the center to the center. So I've made C a lot smaller. And what that does is, sorry, doesn't matter, you missed my egg drawing. So the center, so what I've done here is I shrunk down C, and this is going to end up making it more circular. So what we get here as C goes to 0, you end up becoming a perfect circle. So as I make C smaller and smaller and smaller, I end up getting more of a circular orbit. Conversely, I should move this over so I can get all this on the board. So for C, this is just one concept to really think about, because it's more circular. So if I look back at, and I'm really moving this camera around. So if I look back at my eccentricity definition, C over A, if this is 0, this eccentricity goes to 0. Okay, so the max it can be then is going to be A. And why? Because that's going to equal 1. So if I make C bigger, then this is a really poorly drawn ellipse, sorry about that. Then I've really made this distance, C from the center, I've made that really large relative to the, again, sorry about that. But I've made this distance much larger than the distance between the foci much larger, and this is really a poor comparison, but the focus would be like here, probably. And you end up getting closer to a straight line, is kind of my point here. Like if you make C really large, you end up with sort of a straight line, so it becomes more eccentric, more elliptical. So I'm going to just do E equals C over A again. So we got 2 points on here. All right, we got 2 things to say here. We had one condition where when C went to 0, we had nearly a perfect circle. And as C went to A, we had nearly an extreme ellipse or almost straight line. So I'll put almost straight line. Why don't I just say highly elliptical? That's probably better to say highly elliptical. Highly elliptical orbit. So the max this can be is going to be 1. The max this can be, or then 0, right? So E is going to be Y1, you get A over A. Okay. So E ranges from, so 0 is less than equal to E, which a perfect circle is not really possible, but you can imagine that maybe it is. Neither is really 1 with this. So E is always going to be between 0 and 1. That is an important thing to remember. Okay, so eccentricity defines whether it's circular or elliptical, right? So if I say E is small, let's just say I take 2 E's, and I have one that's 0.07, okay? And I have another that's 0.50. So I've got these 2 E's. Which one is more circular? Think about that for a second. Well, if I got a smaller E, I've got it closer to 0, I've got more circular. All right? If I've got a bigger E, I've got it closer to 1 than the other one. So this one goes to 1, so I should say as C goes to 1. That'll make it a little bit more clear. As C goes to 1, then I get more of an elliptical orbit. So these conceptually would be something like this would be very circular. This one would be that's a pretty big eccentricity. So this is more elliptical, this is more circular. So conversely, if I could ask, well, which one is more elliptical, you would say, well, this one's more elliptical because it's closer to 1. if I said which one's more circular, so it's really a word thing here, then I would say this one's more circular because it's got a lower eccentricity. So the point is, the point is that this E equals C over A, this will really help you kind of understand that a more elliptical orbit and how this relates to how planet movement goes, which I'll explain in a little bit. But I want to say one more thing. Okay, so if you're actually doing this measurement where you take tacks and you put the tacks on each one and you fasten a string to them and go all the way around so that they're fixed to this and the string can only go so far. If you're actually taking this measurement, here's a handy thing to remember. So this distance here is to the center of the circle, recall. So if I take this whole distance here and I have 2A, then I can find the center. So my actual A, so I can measure all the way across the ellipse. So I take a ruler and I measure all the way across here, okay? But I want A, because I want to calculate A. So what I can do then is measure this whole thing and divide it by 2. And that will give me A. So that is one thing you can remember, okay? And the next thing is, when you have this going on, I'm saying this because we're going to do this in lab, but when you have this going on where you have several of these, it can be hard to determine where the center is in between the two focus as well. And that's why I'm talking about how to get to the center here. But if I take this distance, this measurement is going to be 2C. So if I want to find C, I can just measure the distance between the two focus and then divide by 2. And that'll put me right in the center, and that'll give me my C. 2C over 2 is C, right? So if I measure the distance between two focus, divide by 2, then I get C. If I take the measurement across the whole thing, which is the squashed part, the major axis, if I take the measurement of that whole thing, divide by 2, I get A. Then I can calculate the eccentricity, and then I can talk about whether it's more circular or more elliptical. Kepler's second law was probably one of the bigger breakthroughs that he made, first to determine that they were ellipses, but his second law is that planets sweep out equal areas in equal times. So just a brief explanation of how that goes is I'm going to take a planet at 4 different points in its orbit, just a very elliptical planet. Actually, this is probably more like a comet because the planets don't have that elliptical of orbits, but comets can be extreme. Okay, so I was talking about the eccentricity before, where if it's closer to 1, then it's more elliptical. If it's closer to 0, then it's circular. The planets can range, like Neptune's very small. It's like the eccentricity is like 0.0007 or something like that. And Halley's Comet's really large. It's got a 0.87 eccentricity, sorry. But it's got a really, really large one, so it's really elliptical. So it really has a really, really elliptical orbit. But this has great implications as to how fast the planet travels during certain periods of its orbit. Just quickly, I'll just say, when you're far away, there's a point farthest away. That's the perihelion. So that's the farthest away, and when you're the closest point to the object you're orbiting, that's the aphelion. So I'm just going to take the sun. Now, moons work this way too. Like our moon obeys Kepler's laws. Jupiter's moons obey Kepler's laws. Basically, any body rotating around another body obeys Kepler's laws. So let's just look at this one. So I'm going to look at this planet from two consecutive days, we'll say. This is really poor. It's really poor to say. But I'm going to say this over the same period of time here as I am here. So it traveled from here to here in the first case. So in the first case, if I look at the area, and we'll call this A1, it's going to sweep out this really narrow band, but this is farther away, so this is taking up more area. And that's from this time to this time. Now I look over the same time period later in its orbit when it's actually closer to the sun. So I'm going from here to here when it's closer to the sun. Now if I look at the area here, that's underneath this curve, it looks like a bigger slice, but recall it's earlier. So these are supposedly, I'm sure if I measured this I drew it a little bit off, but let's call this one A2. So here's the key here. Here's the key. This area does equal this area if this was drawn perfectly and I measured everything out. So this area, because it's gonna travel really slowly out here, and that's where we're getting to. Travels really slowly and it sweeps out this area in between the sun and this orbit, and this orbital plane, or and in this section, this also sweeps out a very. This is gonna have to speed up now to equal that amount of area. So this is traveling a greater distance on its path. That's the word I was looking for a second ago. So it has to travel slow in order to meet that path. Here it has to travel fast to meet that path. And why do I keep saying has to, blah, blah, blah? It's because the law of equal areas and equal times. So the planets sweep out equal areas in equal times. That is the definition of Kepler's second law. So what does this mean? Well, what this means is that the planet has to slow when it's out here, gets faster, 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 faster. When it gets here, it starts really swinging around. So as it gets closer, it speeds up. As it gets further away, it slows down. So if I was to try to get the actual pace, I'd be going slow, quickly, fast, slow again, quickly, fast, slow, quickly, fast around. So it speeds up as it gets closer to this, as it gets closer to whatever object it's rotating around. Okay? So this is a very important thing. I mean, we use this to slingshot satellites into the outer solar system, like New Horizons did a bunch. They got a bunch of, they call it gravitational assists along the way by swinging around Earth and then swinging around Jupiter, and it got a boost of speed by doing that. Also, one other thing is, like, if astronomers are studying asteroids and comets and stuff like that, they can tell where it is in its orbit. They can tell if it's heading out towards the outer solar system and if it's slowing down. So if they measured it one night and then they measured a couple nights later and they realize that it's slowing down over time, then they know it's going outward bound on its orbit. If it's coming in, it's going to speed up more and more as it comes in, and they can tell that because it's got to obey Kepler's laws. So the conclusion to this is, let's call this point the perihelion. Well, let's not get. So if a planet is further away, let's keep this simple. Not use big words like perihelion and aphelion. So further away, they move slower. Closer, they move faster. So if I were to ask you, at this point, point 1, and point 2, I could say which one is faster? Which one is the planet's orbital velocity? So how fast it's going around on its path. Which one is moving faster? This is further away, so it's going to move slower. This is closer, so it's going to move faster. And really, just so I'm probably confused quite a bit here. This lecture sometime. So what I can talk about here then, I didn't write this and I meant to do this. So that equal times T1 equals T2 equal areas. Okay. So I realized I didn't put that on there. But my point is, at these two different points, that in order to cover this smaller little area here, it's got to move slower. In order to cover the large area, it's got to move bigger, or it's got to move faster. One of the misconceptions that I always see, and I probably will still see it, and I have never figured out a way around it, is people think that a planet is faster if it's more elliptical. So if they look at eccentricity and they say, I have an eccentricity of that, and I have an eccentricity, and I'm just going to do Halley's Comet and Neptune or whatever. If they look at this and they say, oh yeah, one's faster because it's more elliptical, that's not necessarily true. It really, really is not true at all. Just because it speeds up over here, you have to remember that it has to also slow down over here. So it speeds up and then it slows down as it comes out here, and then it averages out. So a planet doesn't get faster just because it's more elliptical. At a point in its orbit, it's moving faster when it's more elliptical. And at a point in its orbit, it's moving slower when it's more elliptical. But the entire orbit is you got to take into account. So just because it's elliptical doesn't mean it's going to be faster. You can have a circular orbit that's really close to the sun, like Earth. Earth's pretty circular orbit. It's elliptical though. Don't confuse that. But it's an elliptical orbit, right? And then if you get something really eccentric, but it's way out in the solar system, that's going to move a lot slower out there than it is inside the solar system, because the planet inside is going to be closer to the sun the whole time. The planet outside is going to be farther away from the sun the whole time. So try not to confuse that. It's just at points, when is it moving faster and when is it moving slower. It's moving slower here, it's moving faster there, and I'm sort of beating this to death. Finally, we get to Kepler's third law. This was actually the most important one that he had come up with. This kind of verified everything else he was saying, because it could make predictions. And this one was the period squared equals the semi-major axis of the planet's orbit cubed. Okay, so that looks kind of weird to you with these exponents, but if this is in AU and this is in years, why don't you say in years there? If this is in AU and this is in years, this actually works out. If you have like kilometers and stuff like that, you need some constants in there to account for that. So the period of the orbit, that is, let's talk about period for a second here. So if I've got a sun in the center, I've got a planet out here, rotating around. The period is from when it starts at this point, and again, I'm really sloppy today, folks. So if I go from this point here, and I go all the way around once, that is its period. That's it, how long does it take to go completely once around the sun? Okay, so this is related to its semi-major axis. And just to remind you what the semi-major axis is, just to remind you quickly over here, the semi-major axis, which we talked about in the ellipsis part, so I've got two foci here, so let's call this the focus. This is the semi-major axis, this to the center. So if I go from the center to here, I go to the edge to here, where this whole thing is the major axis. Okay, so this is A. This is the A that I'm talking about. And this is the average distance. This is the average distance that the planet is for the sun over the course of the whole thing. Sometimes it's really far away, sometimes it's close. This will end up being the average distance. So by knowing the semi-major axis, or even by knowing the period, you can figure out how far a planet is away if you know the period. So like when they do planet hunting, and they're looking at other solar systems, if they can determine the period of the planet, they know how far away it is from the host star. So when you read reports about exoplanets, that's how they know. That's how they know the period is this p squared equals a cubed thing that Kepler came up with in like 1600 or something like that. So it's this a is going to determine its period. Its period is also going to determine its a. So if I have a large a, so I'm a planet way far away, so like my average distance from the sun is huge, so this thing is let's just look at let's just take a second planet further away, okay? This is planet 2, and it goes all the way around like this, okay? If this A is big, then this period is going to be bigger. So it's going to take longer because it's farther away. Key word there, key point there. It's further away, it's got a much bigger area to travel. It's also moving slower based on the Kepler's second law. It's moving slower while it's out here. It's got more distance to travel. It's going to take a lot longer, and that's why you get periods of like, I think Jupiter's like 5 years. Earth is like 1 year. Venus and Mercury are less than a year each. So this is all related to this a cubed thing. It's average distance from the sun. So the closer you get, the faster the period, the faster it's going to move, and the period is going to be a lot faster because it's got a short distance to cover. And if you get outward, it's going to move a lot slower because the a is bigger. So smaller a, smaller p. Bigger a, bigger p. So let's just look at that just one last second here before I move on from this poorly planned lecture. Sorry about that, but it'll hopefully help you a little bit. So P, if I just take this and I solve for P, I'm going to have the square root of A cubed. So if I get a large A, I cube it and have a huge number, and I take the square root of it, that's going to give me the P. If I have a really small a, like Mercury's got a really small a, I cube it, I take the square root, that's going to give me P, and it's going to be much smaller than if I had a really large a. Okay, so this is a really powerful law to, Kepler's third law is a powerful law I just explained with like solar planets, exoplanets I should say, and also it was the key to proving the heliocentric model, which is the sun-centered solar system. It was the key to that because by knowing this, he could predict where the planet would be at a future time. By actually having a way to relate to it mathematically, this proved what he was saying, that planets move in ellipses, that they move in equal areas and equal times. This essentially said, hey, on this date, Jupiter is going to be located here. On this date, Mars is going to be located here, and it's going to follow this mathematical law, and it's all related to the ellipses. So this was actually, to me, probably the succession of events from Copernicus to Tycho Brahe's measurements to Kepler, who worked under Tycho Brahe, coming up with his laws, and then Galileo started working a little bit on physics, and then finally Newton came around and put it all together using gravity to explain all this, which don't worry about that right now. And right now, just don't think about that. Just like follow these laws. We'll get into gravity later. But when Newton came along and explained it with gravity, he had to invent mathematics to do this. And what happened was he ended up starting physics as we know it today. I mean, he revolutionized the world. So all this technology we use and all these other things today, they all started pretty much with Newton. But this started with those guys. This started with just knowing that we were at the center of the universe. I mean, some could argue against me, but in my opinion, it's the most important development in the history of science and the history of our philosophy as far as where we're at in the cosmos. And that's might be in my opinion, but maybe you don't connect the dots between your cell phone and this, but really this, in fact, your cell phone's connecting to satellites in the sky that operate under these laws too. So, but really, I'm saying this development here, it invented physics, it invented the science that we know. I mean, Galileo's played a part by inventing the telescope as well and putting down some of the first laws of physics or whatever. But it's really strange, it may seem like a big leap to say, well, does the sun rotate around the Earth or does the Earth rotate around the sun? It was a big leap to figure out that complex problem. And boy, that just changed the entire worldview that we have and take for granted today.